In the vast, silent theater of our solar system, beyond the familiar orbits of the rocky inner worlds, where the sun's light begins to fade and the temperature plummets to unimaginable lows, lies a frontier unlike any other. It's a realm where the rules of planetary formation seem to bend, where the very composition of matter takes on an alien form, and where the sheer scale of existence dwarfs anything we experience on our homeworld. This is a journey to the outer reaches, a voyage to the edge of our solar system's known world. Lies a realm of unimaginable scale and breathtaking beauty, a place where colossal spheres of gas and ice dominate the landscape, their swirling atmospheres painted with hues unseen on Earth. It's a region of constant twilight, where the sun appears as a distant yet still potent beacon in the inky blackness of space. Here, the planets are not mere points of light, but complex, dynamic systems, each a world unto itself, teeming with mysteries waiting to be unraveled. This is the domain of the giants, a kingdom ruled not by solid ground, but by immense gravitational forces and swirling clouds of hydrogen, helium, and other exotic compounds. These are the behemoths of our solar system, the planetary heavyweights that hold sway over vast swaths of space, their influence felt across billions of kilometers. Four colossal worlds, fundamentally different from our own, wander through the cold, deep dark. They are solitary sentinels, each a unique expression of planetary evolution, shaped by the harsh conditions of the outer solar system. Unlike the terrestrial planets, forged from rock and metal, these giants are composed primarily of gas and ice, their cores hidden deep within layers of immense pressure and exotic materials. They are Jupiter, the undisputed king of the planets, a swirling maelstrom of colorful clouds and powerful storms, a world so massive that it could contain all the other planets in our solar system combined. Jupiter's Great Red Spot, a storm that has raged for centuries, is a testament to the planet's immense power and dynamic atmosphere. Saturn, the jewel of the solar system, adorned with its breathtaking rings, a celestial masterpiece composed of countless icy particles, each reflecting sunlight like a tiny mirror. Saturn's rings are not a solid structure, but a dynamic and ever-changing collection of debris, constantly colliding and interacting, creating a spectacle of unparalleled beauty. Uranus, the sideways planet, tilted on its axis, presenting a unique perspective to the sun, a serene blue sphere shrouded in a hazy atmosphere, hiding a turbulent interior. Uranus's unusual tilt is believed to be the result of a massive collision early in its history, a cataclysmic event that forever altered its orientation. And Neptune, the distant, enigmatic blue giant, whipped by supersonic winds, a world of perpetual twilight, its atmosphere a swirling tapestry of methane clouds. Neptune's Great Dark Spot, a storm similar to Jupiter's Great Red Spot, was once a prominent feature of its atmosphere, but has since disappeared, highlighting the dynamic and unpredictable nature of these giant planets. Planets not of solid ground, but of swirling gases and exotic ices, each a universe unto itself. They are dynamic, ever-changing environments, where storms rage for centuries and winds reach unimaginable speeds. Their atmospheres are layered and complex, with different regions exhibiting distinct temperatures, pressures, and compositions. These are worlds that defy easy categorization, challenging our understanding of planetary science. They are titans of such immense proportions that they collectively dwarf all other planetary bodies in our celestial family, holding sway over a vast expanse of space. Their gravitational influence shapes the orbits of countless asteroids, comets, and even other planets, acting as cosmic shepherds, guiding the movements of celestial bodies throughout the solar system. Their sheer size is a testament to the power of accretion and the abundance of gas and ice in the outer solar system. Their existence and their unique characteristics challenge our very definition of what a planet can be, pushing the boundaries of our scientific understanding and inspiring us to look deeper into the cosmic ocean. They force us to reconsider our assumptions about planetary formation, atmospheric dynamics, and the potential for life beyond Earth. By studying these giants, we gain a deeper appreciation for the diversity and complexity of the universe. These are not the quiet, barren landscapes of Mars or the scorched surface of Mercury. They are not worlds of solid rock and dusty plains, where the pace of change is slow and deliberate. The inner planets, with their relatively thin atmospheres and solid surfaces, offer a stark contrast to the dynamic and turbulent environments of the gas giants. Instead, they are dynamic, chaotic worlds of perpetual motion. A constant ballet of swirling gases, powerful storms, and ever-shifting cloud patterns. The energy that drives these atmospheric phenomena is immense, fueled by the planet's internal heat and the faint sunlight that reaches them from the distant sun. Imagine atmospheres deeper than Earth's oceans, with storms larger than our entire planet that rage for centuries. These are not fleeting squalls or localized weather events, but colossal, persistent features that dominate the planetary landscape. The Great Red Spot on Jupiter, for example, has been observed for over 300 years, a testament to the planet's immense power and the longevity of its atmospheric phenomena. Picture majestic rings, crafted from countless particles of glistening ice, forming halos of ethereal light around their colossal parent bodies. These rings are not solid structures, but vast collections of individual particles, ranging in size from tiny grains of dust to massive chunks of ice. They are constantly colliding and interacting, creating a dynamic and ever-changing spectacle. These are worlds surrounded by their own miniature solar systems, with dozens of moons that are just as fascinating and diverse as the planets they orbit. Each moon is a unique world, with its own geological history, surface features, and potential for harboring life. These moons are not merely passive satellites, but active participants in the complex dynamics of the outer solar system. From volcanic infernos like those found on Jupiter's moon Io, the most volcanically active world in the solar system, where molten rock erupts from the surface in spectacular displays of geological power. Io's volcanoes are fueled by tidal forces generated by Jupiter's immense gravity, constantly squeezing and stretching the moon's interior. To frozen worlds hiding vast subsurface oceans, like Europa and Enceladus, where liquid water may exist beneath thick layers of ice, potentially harboring life in the dark depths. These subsurface oceans are kept liquid by tidal heating, a process similar to that which fuels Io's volcanoes, but on a much grander scale. These moons represent some of the most compelling targets in our search for life beyond Earth, offering tantalizing hints of habitable environments in the most unexpected of places. The discovery of water plumes erupting from Enceladus's south pole has provided direct evidence of a subsurface ocean, making it a prime candidate for future exploration. Our journey to these distant worlds is a story of human ingenuity and relentless curiosity. For millennia, they were merely wandering stars in our night sky, their true nature a complete mystery. Ancient astronomers observed their movements, meticulously charting their paths across the heavens, but their composition and characteristics remained unknown. It was only with the dawn of the space age that we began to pull back the veil. Robotic emissaries, our proxies in the cosmos, have traversed billions of kilometers of interplanetary space to give us our first close-up views of these magnificent giants. These spacecraft, equipped with sophisticated instruments, have braved the harsh conditions of the outer solar system to gather data and images that have revolutionized our understanding of these distant worlds. Each mission has returned images and data that have consistently overturned our expectations, revealing worlds far more complex, active, and wondrous than we'd ever dared to imagine. The Voyager missions, in particular, provided our first detailed views of the gas giants and their moons, revealing a level of complexity and diversity that was previously unimaginable. This exploration has transformed them from distant points of light into living, breathing laboratories of planetary science. We can now study their atmospheres, magnetic fields, and internal structures in unprecedented detail, gaining insights into the fundamental processes that shape planetary evolution. This documentary is an invitation to journey to that distant frontier. We will venture far beyond the asteroid belt, into the cold heart of the outer solar system. We will embark on a virtual voyage, guided by the latest scientific discoveries and stunning visualizations, to explore the wonders of these giant planets. We will explore the swirling cloud tops of Jupiter, marveling at the intricate patterns and vibrant colors of its atmosphere, and delving into the mysteries of its great red spot. We will examine the planet's layered atmosphere, from the upper reaches of the cloud tops to the deeper regions where exotic compounds may exist. Dive through the magnificent rings of Saturn, witnessing the breathtaking beauty of these icy structures up close and learning about their formation and evolution. We will explore the different regions of the rings, from the dense A ring to the faint F ring, and examine the complex interactions between the ring particles, and glide past the mysterious blue orbs of Uranus and Neptune, unraveling the secrets of their unique atmospheres and exploring their hidden depths. We will investigate the causes of their blue color and examine the role of methane in their atmospheres. We will investigate their formation, exploring the processes that led to the creation of these giant planets in the outer solar system. We will delve into their turbulent weather, examining the forces that drive their powerful storms and winds. We will study their powerful magnetic fields, which protect them from the solar wind and create spectacular auroras. And we will explore their incredible families of moons and rings, each a unique world with its own story to tell. By studying these giants, we not only learn about the distant corners of our own solar system, but also gain profound insights into the formation and evolution of countless other planetary systems scattered throughout our galaxy, helping us to place our own world into a grander cosmic context. The gas giants of our solar system serve as a crucial benchmark for understanding the diversity of exoplanets that have been discovered in recent years. By comparing and contrasting our own gas giants with these distant worlds, we can gain a better understanding of the processes that shape planetary systems throughout the universe. This journey to the frontier of Titans is not just about exploring distant worlds. It's about understanding our place in the cosmos and pushing the boundaries of human knowledge. To truly understand the stark differences that set the outer planets apart from their inner, rocky counterparts like our own Earth, we need to embark on a journey of cosmic proportions. We must delve into the very origins of our solar system and unravel the mysteries of planetary formation. What forces sculpted these colossal gas giants, and why did the inner planets remain relatively small and rocky? These are the questions that drive our exploration. To find the answers, we must travel back in time, over 4.5 billion years, to a period when our solar system was nothing more than a nascent dream in the vast expanse of space. It's a journey into the deep past, a voyage to witness the very birth of the worlds we know today. We must return to the birth of our solar system, when all that existed was a vast, swirling cloud of gas and dust, a cosmic soup of raw materials known as the solar nebula. This nebula was the cradle of our planetary system, the birthplace of everything from the smallest asteroid to the largest gas giant. Imagine a colossal, rotating disk stretching across unimaginable distances, filled with the building blocks of worlds. At its center, immense gravitational pressure ignited a star, our Sun. This cataclysmic event marked the beginning of a new era, as the Sun's radiant energy began to shape the destiny of the surrounding nebula. The ignition of the Sun was a pivotal moment, a cosmic fire that forged the future of our solar system. In the regions closest to this newborn star, temperatures were incredibly high, a scorching inferno that would dictate the composition of the planets that would eventually form there. The inner solar system was a crucible where only the most resilient materials could survive. The intense heat vaporized lighter elements and compounds, turning them into gases and blowing them away into the farther, colder reaches of the nebula. This process of evaporation and dispersal played a crucial role in shaping the composition of the inner and outer solar system. The Sun's powerful winds acted as a cosmic sculptor, carving out the destinies of the planets to come. Only heavy, rocky materials and metals could endure the inferno, slowly clumping together through gravitational attraction to form the small, dense worlds we know as Mercury, the swift and heavily cratered planet closest to the Sun, a world of extreme temperatures and desolate landscapes. Its proximity to the Sun has made it a planet of extremes, a testament to the harsh conditions of the inner solar system. Venus, a scorching, cloud-covered world with a toxic atmosphere and a runaway greenhouse effect, a cautionary tale of planetary evolution gone awry. Its thick atmosphere traps heat, making it the hottest planet in our solar system, a stark contrast to its neighbor Earth. Earth, our vibrant blue planet, teeming with life and blessed with a unique combination of conditions that have allowed life to flourish. It is a haven in the vastness of space, a testament to the delicate balance that sustains life as we know it. And Mars, the rusty red planet, a once potentially habitable world that now stands as a cold, arid desert, a reminder of the fragility of planetary environments. Its reddish hue comes from iron oxide, or rust, on its surface, a testament to its ancient past. But further out, beyond the orbit of Mars and the scattered debris of the asteroid belt, a critical boundary existed, a cosmic threshold that separated the inner and outer solar system. This boundary marked a significant shift in temperature and composition, a dividing line that would shape the destinies of the planets beyond. This boundary is known to planetary scientists as the frost line, or snow line, a crucial concept in understanding the formation of the outer planets. It represents the distance from the Sun where temperatures are low enough for volatile compounds to freeze. Here, beyond this invisible barrier, temperatures were low enough for volatile compounds, substances like water, the life-giving substance that covers much of our own planet and exists in frozen form throughout the outer solar system. Water ice is a fundamental building block of many icy moons and planets. Ammonia, a pungent compound of nitrogen and hydrogen that freezes into a solid ice at low temperatures, playing a role in the composition of icy bodies. And methane, a simple hydrocarbon that also freezes into ice, contributing to the icy mantles of distant planets and moons. To freeze and condense into solid ice particles, transforming the composition of the solar nebula in this region. These ice particles would become the seeds of the giant planets. This simple fact of cosmic chemistry, the freezing of volatile compounds, changed everything, setting the stage for the formation of a completely different type of planet. It was a pivotal moment in the history of our solar system. Suddenly, the raw material available for building planets was not just rock and metal, the limited resources of the inner solar system, but also vast quantities of ice, an entirely new source of planetary building blocks. This abundance of ice would fuel the growth of the gas giants. In fact, ice was far more abundant than rock and metal in the outer solar nebula, making it the dominant material for planetary formation in this region. The outer solar system was a treasure trove of icy resources, providing a massive reservoir of building blocks for planetary formation to draw upon, setting the stage for a different class of planet to emerge, planets unlike anything found in the inner solar system. These would be the gas giants, the behemoths of our solar system. This abundance of icy material allowed planetary cores to grow much larger and much faster than their rocky counterparts in the inner solar system, giving them a significant head start in the race to become planets. The icy building blocks provided a rapid pathway to planetary growth. These embryonic planets, sometimes called protoplanets, quickly swelled to masses many times that of Earth, becoming gravitational powerhouses in their own right. They were on their way to becoming the gas giants we know today. As they grew, their gravitational pull became increasingly powerful, extending their reach and influence over the surrounding nebula. Their growing gravity was a key factor in their ultimate success, allowing them to attract and hold on to the most abundant elements in the entire nebula, the light gases that made up the bulk of the solar system's mass. This was the turning point in their evolution. Hydrogen, the simplest and most abundant element in the universe, the fuel that powers stars and the primary component of the gas giants. And helium, the second lightest element, another major constituent of the Sun and the gas giants, a noble gas that is resistant to chemical reactions. These are the lightest and most common gases in the universe, the very same elements that fueled the Sun, now being captured by the growing outer planets. The gas giants were essentially miniature versions of the Sun in terms of their composition. The inner planets were too small and too hot to retain these light gases, which escaped back into space, leaving them with thin atmospheres or none at all. The inner planets simply lacked the gravitational muscle to hold onto these gases, but the giant cores of the outer planets had no such problem, their immense gravity easily capturing and holding on to these precious gases. they were poised to become gas giants. This process, known as core accretion, triggered a runaway effect, a positive feedback loop that accelerated the growth of the outer planets. It was a snowball effect that led to their immense size. The more hydrogen and helium a protoplanet captured, the more massive it became, increasing its gravitational pull and its ability to capture even more gas. It was a self-reinforcing cycle of growth. The more massive it became, the stronger its gravity grew, allowing it to capture even more gas, creating a powerful gravitational feedback loop that fueled its rapid expansion. This feedback loop was the key to their transformation into gas giants. This feedback loop led to the rapid and monumental growth of the outer planets, transforming them from icy cores into colossal gas giants in a relatively short period of time, which ballooned into the behemoths we see today, the gas giants that dominate the outer solar system with their immense size and powerful gravity. They became worlds composed primarily of the same primordial materials as the Sun itself, hydrogen and helium, with traces of other elements and compounds. They are essentially giant balls of gas, with perhaps a small rocky core deep within. Fundamentally different in composition, structure, and scale from the small, terrestrial worlds of the inner solar system, a testament to the different conditions and processes that shaped their formation. The gas giants and the terrestrial planets represent two distinct classes of planets. Their formation beyond the frost line is the key to their identity as giants of gas and ice, a cosmic boundary that determined their composition and ultimately their destiny. The frost line is the dividing line between the rocky inner planets and the gas and ice giants of the outer solar system. While all four outer planets are giants, they are not all the same. These colossal orbs, residing far beyond the asteroid belt, present a fascinating study in contrasts. Each possesses unique characteristics, a testament to the diverse conditions and processes that shaped them billions of years ago. From their atmospheric compositions to their internal structures, the gas giants and ice giants offer a compelling glimpse into the complexities of planetary formation. Our journey through the outer solar system reveals two distinct categories of colossal worlds, a division that tells a deeper story about their individual formation histories. We'll delve into the fundamental differences between these planetary siblings, exploring the factors that led to their divergent paths. Understanding these differences is crucial to unraveling the mysteries of how planetary systems, including our own, come into being. The story of the gas giants and ice giants is a story of cosmic evolution, a tale written in the very fabric of these distant worlds. The first two giants we encounter, Jupiter and Saturn, are known as the gas giants. These behemoths dominate the outer solar system, their immense gravitational pull influencing the orbits of countless smaller bodies. Their swirling atmospheres, vibrant colors, and intricate cloud patterns are a constant source of wonder, captivating astronomers and space enthusiasts alike. Jupiter, the king of the planets, and Saturn, with its majestic rings, represent the epitome of gas giant evolution. They are the true heavyweights of our solar system, composed almost entirely of hydrogen and helium, the lightest elements. These are the same elements that fuel the stars, giving Jupiter and Saturn a composition remarkably similar to that of our Sun. However, unlike stars, they lack the mass necessary to ignite nuclear fusion in their cores. Instead, they remain in a perpetual state of gaseous existence, swirling masses of hydrogen and helium under immense pressure. Their structures are more akin to stars than to rocky planets like Earth. Imagine a world without a solid surface, a planet where the atmosphere gradually transitions into a dense, fluid ocean of hydrogen and helium. This is the reality of Jupiter and Saturn, worlds that challenge our conventional understanding of planetary structure. Their internal dynamics are complex and poorly understood, but scientists believe that powerful magnetic fields and swirling currents play a crucial role in shaping their atmospheres. They possess enormous, dense cores deep within, but the bulk of their mass is contained within vast, deep atmospheres that transition seamlessly from gas to a liquid state under immense pressure without a solid surface to stand on. The pressure at the heart of these gas giants is so extreme that it can compress hydrogen into a metallic state, a bizarre form of matter that conducts electricity like a metal. This metallic hydrogen is thought to be responsible for generating the powerful magnetic fields that surround Jupiter and Saturn, shielding them from the constant barrage of solar wind particles. Further out, in the cold, dim frontiers of the solar system, we find Uranus and Neptune. These distant worlds, shrouded in mystery and bathed in faint sunlight, represent a different class of giant planets. Their blue hues, a result of methane in their atmospheres, hint at the unique composition and conditions that prevail in this remote region of our solar system. Exploring Uranus and Neptune is like venturing into an alien realm, a place where the laws of physics seem to operate under different rules. These two planets are known as the ice giants. This designation reflects the significant proportion of icy materials, such as water, methane, and ammonia, that make up their internal structure. Unlike the gas giants, which are primarily composed of hydrogen and helium, the ice giants are a complex mixture of elements and compounds, a testament to the diverse building blocks that were available in the outer reaches of the early solar system. While they are still enormous compared to Earth, they are significantly smaller and less massive than their gas giant cousins. Uranus and Neptune occupy a middle ground between the terrestrial planets and the gas giants, showcasing the wide range of planetary sizes and compositions that exist in our solar system. Their smaller size and lower mass have profound implications for their internal structure, atmospheric dynamics, and overall evolution. Like Jupiter and Saturn, they have extensive atmospheres of hydrogen and helium. However, the key difference lies in what's beneath those atmospheres. While hydrogen and helium are still present in abundance, the ice giants possess a much larger proportion of heavier elements and compounds, giving them a distinct chemical signature. This difference in composition is a crucial clue to understanding their formation history and the conditions that prevailed in the outer solar system billions of years ago. A much larger proportion of their total mass is made up of heavier elements, specifically the ices for which they are named: water, methane, and ammonia. These icy compounds exist in a hot, dense, fluid state within the ice giants, forming a vast ocean that surrounds their rocky cores. The interaction between this icy mantle and the atmosphere above is thought to drive the complex weather patterns and magnetic fields that characterize Uranus and Neptune. These compounds, which were so abundant beyond the frost line, form a hot, dense, fluid mantle around a small, rocky core, giving these worlds a fundamentally different internal structure and composition. The frost line, a critical boundary in the early solar system, marks the distance from the sun where volatile compounds like water, methane, and ammonia could condense into solid ice. Beyond this line, these ices became readily available as building blocks for planet formation, leading to the creation of the ice giants. This divergence between gas and ice giants likely comes down to timing and location. The story of their formation is a tale of cosmic competition, where the availability of resources and the speed of accretion played a crucial role in determining their ultimate fate. Understanding the interplay between these factors is essential to unraveling the mysteries of planetary formation and the diversity of worlds that exist in our galaxy. Jupiter and Saturn formed closer to the Sun, in a region of the early solar nebula that was denser with gas. They grew large and fast, allowing them to sweep up enormous quantities of hydrogen and helium before the young Sun's solar wind blew the remaining primordial gas out of the system. Their proximity to the Sun and their rapid growth gave them a significant advantage in the race to acquire gas, transforming them into the gas giants we know today. They were the firstborn giants, growing to their immense sizes in a relatively short period of planetary history. Their rapid growth allowed them to dominate the gas-rich environment of the early outer solar system, becoming the massive worlds we see today. They essentially won the planetary formation lottery, securing the lion's share of the available gas and establishing their dominance over the outer solar system. Uranus and Neptune, on the other hand, formed further out in the solar system, where the solar nebula was less dense and orbital times were much longer. In this remote region, the pace of planet formation was significantly slower, and the availability of gas was much more limited. This slower growth rate had a profound impact on their ultimate size and composition. The process of building their cores took more time. By the time they grew massive enough to begin gravitationally capturing large amounts of hydrogen and helium, much of that gas had already been cleared away from the solar system. The solar wind, a stream of charged particles emanating from the sun, played a crucial role in dispersing the remaining gas in the outer solar system, effectively starving Uranus and Neptune of the raw materials they needed to become true gas giants. As a result, they ended up with far less massive gaseous envelopes compared to Jupiter and Saturn, and a much higher proportion of the icy materials that made up their initial cores. They became the ice giants, worlds rich in water, methane, and ammonia, a testament to the unique conditions that prevailed in the distant reaches of the early solar system. They are still giants, but they represent a different, less gas-rich pathway of planetary formation in the far reaches of our celestial neighborhood. The story of Uranus and Neptune is a reminder that there are many different ways to build a planet, and that the diversity of worlds in our solar system is a reflection of the complex and chaotic processes that shaped them billions of years ago. Their existence expands our understanding of planetary formation and highlights the potential for even more diverse planetary systems throughout the universe. As we embark on this cosmic voyage, our first destinations in this grand tour are the two undisputed kings of our solar system, Jupiter and Saturn. These celestial behemoths dominate the outer reaches of our planetary neighborhood, beckoning us with their swirling clouds and enigmatic secrets. They are the giants that hold sway over the solar system. These are the gas giants, worlds of such staggering scale that they almost seem to defy comprehension. Their sheer size dwarfs anything we know on Earth, challenging our perceptions of planetary possibility. They are not merely large, they are colossal, representing a different order of magnitude in planetary existence. We struggle to grasp the immensity of these worlds, their vastness stretching the limits of our imagination. Jupiter, the larger of the two, is a monster. A swirling, turbulent giant, it commands attention with its vibrant bands of color and the ever-present Great Red Spot, a storm that has raged for centuries. It is a world of extremes, a place where gravity reigns supreme and atmospheric forces collide in spectacular fashion. It is so massive that it contains more than twice the mass of all the other planets, moons, asteroids, and comets in the solar system combined. Imagine gathering all the other celestial bodies in our solar system: Mercury, Venus, Earth, Mars, Uranus, Neptune, their moons, the asteroid belt, and countless comets. And they would still pale in comparison to the sheer bulk of Jupiter. Its gravitational influence is felt throughout the solar system, shaping the orbits of other planets and influencing the distribution of asteroids and comets. If Jupiter were a hollow shell, you could fit all the other planets inside it with room to spare. This simple thought experiment highlights the truly astonishing scale of Jupiter. It's a testament to the power of accretion and the dominance of gravity in the formation of our solar system. The very idea of fitting all those worlds within its confines is mind-boggling. This sheer size gives it an immense gravitational influence, a force that has shaped the architecture of our entire solar system for billions of years, acting as both a shepherd and a protector for the inner worlds. Jupiter's gravity has cleared out debris from the inner solar system, preventing potentially catastrophic impacts on Earth and the other terrestrial planets. It has also sculpted the asteroid belt, preventing it from coalescing into a planet. In essence, Jupiter acts as a cosmic bodyguard, shielding us from harm. Its presence has been crucial for the development of life on Earth. Saturn, while smaller and less massive than Jupiter, is no less spectacular. It possesses a unique allure, a captivating beauty that sets it apart from its larger sibling. While Jupiter commands respect through its sheer size, Saturn enchants with its ethereal rings and serene atmosphere. It is a world renowned for its breathtaking system of rings, an iconic feature that makes it one of the most recognized and beloved objects in the night sky. These rings, composed of countless icy particles, create a dazzling spectacle that has captivated astronomers and stargazers for centuries. They are a testament to the beauty and complexity of the universe, a reminder that even in the vastness of space, there is room for elegance and grace. The rings are not solid structures, but rather a collection of individual particles, each orbiting Saturn like a tiny moon. While Jupiter is defined by its raw power and mass, Saturn is defined by its elegance and beauty. Jupiter is a force of nature, a cosmic juggernaut that dominates its surroundings. Saturn, on the other hand, is a celestial masterpiece, a delicate and intricate creation that inspires awe and wonder. They are two sides of the same coin, representing different facets of the gas giant archetype. It is the least dense planet in our solar system. In fact, its average density is less than that of water. If you could find a bathtub large enough, Saturn would float. This seemingly impossible feat is due to Saturn's composition, which is primarily hydrogen and helium, the lightest elements in the universe. This low density has profound implications for Saturn's structure and dynamics, influencing its rotation, atmospheric circulation, and magnetic field. This low density, combined with its rapid rotation, causes the planet to bulge significantly at its equator, making it the most oblate or flattened planet in our cosmic family. Saturn's rapid spin, completing a rotation in just over 10 hours, exacerbates this effect, causing the planet to stretch outwards at its equator and flatten at its poles. This distinctive shape is a visual reminder of the powerful forces at play within this gas giant. Despite their differences in size and density, these two giants share a common heritage and fundamental composition. Both are composed primarily of hydrogen and helium, the same basic ingredients that make up the Sun. This shared composition suggests that Jupiter and Saturn formed from the same primordial cloud of gas and dust that gave birth to our solar system. They are, in essence, miniature versions of our Sun, albeit without the nuclear fusion that powers our star. Deep inside, their immense atmospheric pressures are thought to squeeze hydrogen gas into a bizarre state known as liquid metallic hydrogen. This exotic form of matter exists only under extreme pressure, where the hydrogen atoms are forced so close together that they share electrons, allowing them to conduct electricity like a metal. This liquid metallic hydrogen plays a crucial role in generating the powerful magnetic fields of Jupiter and Saturn. This exotic material, which behaves like a molten metal, is believed to be the source of their incredibly powerful magnetic fields. These magnetic fields are thousands of times stronger than Earth's, extending far into space and creating vast magnetospheres that envelop the planets. These magnetospheres act as shields, deflecting harmful solar wind particles and protecting the planet's atmospheres. These magnetospheres are vast, extending for millions of kilometers into space and trapping lethal doses of radiation, creating some of the most hazardous environments in the entire solar system for any visiting spacecraft. Navigating these regions requires careful planning and robust shielding to protect sensitive instruments from the damaging effects of radiation. The intensity of the radiation is so high that it can quickly degrade electronic components, rendering spacecraft inoperable. The atmospheres of Jupiter and Saturn are also laboratories of extreme weather. They are streaked with vibrant bands and zones of clouds, driven by powerful jet streams and swirling storms. These atmospheric features are constantly evolving, creating a dynamic and ever-changing spectacle. The colors of the clouds are due to the presence of various chemical compounds, such as ammonia, sulfur, and water ice, which react with sunlight to produce a dazzling array of hues. Jupiter's Great Red Spot is the most famous of these, a colossal anticyclonic storm that has been raging for at least 4 centuries and is wider than our entire planet. This persistent storm is a testament to the power and longevity of Jupiter's atmospheric dynamics. Scientists are still trying to understand the mechanisms that sustain the Great Red Spot, but it is believed to be fueled by the planet's internal heat and rapid rotation. The Great Red Spot is not a static feature. It changes in size and shape over time, sometimes shrinking and sometimes expanding. Saturn, too, has its own unique atmospheric phenomena, including a bizarre 6-sided jet stream at its north pole, known as the hexagon. This enigmatic feature is a persistent pattern of clouds that encircles Saturn's north pole, maintaining its hexagonal shape for reasons that are still not fully understood. The hexagon is thought to be a result of complex interactions between Saturn's rotation, atmospheric circulation, and magnetic field. It is a truly unique and fascinating phenomenon that sets Saturn apart from other planets in our solar system. These features are windows into the deep, turbulent dynamics of worlds where weather operates on a scale and with an intensity that dwarfs anything we could ever experience here on Earth. The jet streams on Jupiter and Saturn can reach speeds of hundreds of kilometers per hour, far exceeding the strongest hurricanes on Earth. The storms on these planets can last for years, decades, or even centuries, creating a truly alien and awe-inspiring environment. Studying these extreme weather phenomena helps us to better understand the fundamental principles of atmospheric dynamics and climate change, not only on other planets, but also here on Earth. Leaving the familiar warmth and light of the gas giants behind, we venture further into the cold and darkness, a realm where sunlight is a mere whisper and the temperature plummets to unimaginable lows. This is the domain of the ice giants and the distant, icy bodies that populate the outer reaches of our solar system. It's a place of mystery where the rules seem different and the landscapes are sculpted by forces we are only beginning to understand. We journey towards the outer frontiers of our planetary system, a vast expanse that stretches billions of kilometers from the sun. Here, the solar wind weakens and the gravitational influence of our star begins to wane, giving way to the interstellar medium beyond. This is the edge of our known world, a cosmic shore where the familiar gives way to the unknown. Here, in this frigid realm, we encounter the ice giants, Uranus and Neptune. These are not simply smaller versions of Jupiter and Saturn. They are a distinct class of planet, composed of a different mix of elements and possessing unique characteristics that set them apart. They represent a crucial link in our understanding of planetary formation and the diversity of worlds that can exist in the universe. Uranus and Neptune, often spoken of together, yet each possesses its own distinct personality and set of enigmas. They are siblings in the outer solar system, sharing a common heritage but evolving along different paths, shaped by the unique conditions of their environments. These two planets are mysterious, blue-hued worlds that have only been visited once by a spacecraft, the Voyager 2 probe, decades ago. That single flyby provided us with our first close-up glimpse of these distant giants, revealing their beauty and sparking countless questions that continue to drive scientific inquiry today. We eagerly await the day when we can send another mission to explore these fascinating worlds in greater detail. The data Voyager 2 collected remains invaluable, a cornerstone of our understanding of these remote planets. Uranus is the first ice giant we meet, and it immediately presents us with a profound cosmic puzzle. Its pale blue hue hints at the secrets hidden within its atmosphere, while its unusual orientation challenges our understanding of planetary formation and evolution. Unlike any other planet in our solar system, Uranus is tilted on its side, a bizarre anomaly that has baffled scientists for centuries. This extreme tilt dramatically alters its seasons and its interaction with the solar wind, creating a truly unique environment. Its axis of rotation is tipped by an astonishing 98 degrees, a near right angle compared to the orbital plane of the solar system. This means that, at certain points in its orbit, one of Uranus's poles points almost directly at the Sun, meaning it essentially rolls along its orbital path around the Sun like a cosmic bowling ball. This unusual rotation has a profound impact on the planet's magnetic field, which is also tilted and offset from the planet's center. This extreme axial tilt results in the most bizarre seasons in the solar system, a cycle of perpetual daylight and unending darkness that lasts for decades at a time. Imagine living on a world where the sun never sets for a generation, only to be plunged into darkness for an equal length of time. For a quarter of its long, 84-year orbit, one pole is bathed in continuous sunlight, experiencing a summer that lasts for over 20 years. The illuminated hemisphere basks in the faint but persistent glow of the sun, while the opposite side of the planet remains shrouded in shadow, while the other faces decades of complete darkness. Then, the roles reverse, and the hemisphere that was once bathed in sunlight is plunged into a long, dark winter. This dramatic seasonal shift must have a profound impact on the planet's atmosphere and weather patterns. Scientists believe this peculiar orientation is the result of a cataclysmic collision with an Earth-sized protoplanet deep in the solar system's past, a cosmic billiard shot that forever altered the destiny of Uranus. This impact would have been a truly momentous event, reshaping the planet's structure and influencing its subsequent evolution. This violent event would have knocked the young planet over, forever changing its orientation to the Sun and leaving it spinning on its side. The evidence for this collision is compelling, but the details of the impact remain a subject of ongoing research and debate. The atmosphere of Uranus is a serene, pale cyan color, a result of methane gas in its upper layers, absorbing red light and reflecting blue and green wavelengths back into space. This gives the planet its distinctive hue and contributes to its overall sense of tranquility. Compared to the other giants, it appears surprisingly placid, with few visible clouds or storms, giving the impression of a calm and peaceful world. However, beneath this serene exterior, Uranus may harbor hidden depths and complex atmospheric processes that we have yet to fully understand. Recent observations have revealed subtle cloud features and variations in the planet's atmosphere, suggesting that it may be more dynamic than previously thought. Our final major planetary stop is Neptune, the eighth and most distant planet from the Sun, a lonely sentinel guarding the outer reaches of our solar system. It's a world of extremes, where the Sun appears as a distant star and the cold is almost absolute. Despite its immense distance and the faint sunlight it receives, Neptune is a surprisingly dynamic and active world, a testament to the power of internal heat and atmospheric processes. Its turbulent atmosphere and powerful winds defy the expectations of a planet so far from the Sun. It is a vibrant, deep blue jewel, a stunning sight against the black backdrop of space. Its color is both beautiful and mysterious, hinting at the complex chemical processes that occur within its atmosphere. Its color also derived from atmospheric methane, but with a richness that suggests an unknown atmospheric component is also at play, something that enhances the blue hue and sets it apart from Uranus. Scientists are still working to unravel the mystery of Neptune's deep blue color. In stark contrast to the tranquility of Uranus, Neptune is home to the fastest winds in the solar system, a world of constant storms and atmospheric turbulence. These winds are a force to be reckoned with, shaping the planet's appearance and driving its dynamic weather patterns. These winds whip through its atmosphere at supersonic speeds, reaching over 2,000 kilometers per hour, creating a truly awe-inspiring spectacle. The source of these powerful winds is still not fully understood, but they are thought to be driven by a combination of internal heat and the planet's rapid rotation. When Voyager 2 flew by, it witnessed a massive storm system reminiscent of Jupiter's, dubbed the Great Dark Spot, a swirling vortex of clouds that dominated the planet's southern hemisphere. This storm was a dramatic demonstration of Neptune's dynamic atmosphere. The story of Neptune's discovery is itself a triumph of science, a testament to the power of human intellect and our ability to understand the universe through observation and calculation. It's a story that highlights the beauty and elegance of scientific reasoning. It was not found by accident through a telescope, but through the power of mathematics and our understanding of gravity, a remarkable feat of intellectual deduction. This discovery demonstrated the profound connection between theory and observation in science. Astronomers had noticed that Uranus was not moving along its orbit exactly as predicted, a subtle discrepancy that hinted at the presence of an unseen gravitational influence. These deviations from the expected path were the key to unlocking the mystery of Neptune's existence. Its path was being perturbed by the gravitational pull of an unseen object, a massive body lurking in the outer solar system and tugging on Uranus with its invisible force. This gravitational perturbation was the clue that led mathematicians to Neptune. Using Newton's laws, mathematicians independently calculated the location of this mystery planet, predicting its position in the sky with remarkable accuracy. This was a triumph of classical physics, demonstrating the power of Newton's laws to explain and predict the motion of celestial bodies. And when astronomers pointed their telescopes to that spot in the sky in 1846, there it was, a faint but unmistakable disk confirming the mathematical prediction. The discovery of Neptune was a watershed moment in the history of astronomy. Neptune's existence was predicted on paper before it was ever seen, a testament to the predictive power of scientific theory and the ability of mathematics to unlock the secrets of the universe. It stands as a shining example of how science can illuminate the unknown and expand our understanding of the cosmos. The study of Jupiter, Saturn, Uranus, and Neptune is not just about understanding our own celestial backyard. It's about placing our solar system within the grander context of the universe. These gas and ice giants, so different from the rocky inner planets, hold vital clues to the processes that shape planetary systems everywhere. It is also a critical endeavor that provides us with a framework for understanding planetary systems far beyond our own. By studying the architecture and composition of our outer solar system, we gain invaluable insights into the potential diversity and formation mechanisms of exoplanetary systems light years away. This comparative approach is essential for unraveling the mysteries of planet formation and evolution on a cosmic scale. In recent decades, astronomers have discovered thousands of planets orbiting other stars, known as exoplanets. This groundbreaking discovery has revolutionized our understanding of planetary systems, revealing a stunning array of configurations and compositions that challenge our preconceived notions. The sheer number of exoplanets discovered underscores the prevalence of planets throughout the galaxy, fueling the search for potentially habitable worlds beyond our solar system. A great many of these distant worlds appear to be giants, similar in size and mass to the ones we find in our outer solar system. These giant exoplanets, often referred to as hot Jupiters or warm Neptunes, exhibit a wide range of orbital characteristics and atmospheric properties. Their prevalence in exoplanetary surveys highlights the importance of understanding the formation and evolution of giant planets in diverse environments. By studying our own giants up close, we can develop and test models of planetary formation, atmospheric dynamics, and internal structure. Detailed observations of Jupiter, Saturn, Uranus, and Neptune provide crucial constraints for these models, allowing us to refine our understanding of the physical processes that govern the behavior of giant planets. These models can then be applied to interpret observations of exoplanets, shedding light on their composition, atmospheric circulation, and potential habitability, that can then be applied to these far-flung systems that we can only observe as tiny points of light. The faint signals emanating from these distant worlds require sophisticated techniques and powerful telescopes to detect and analyze. By comparing the observed properties of exoplanets with the predictions of our models, we can gain insights into their formation histories and potential for harboring life. Our solar system's giants serve as essential ground truth laboratories. They provide us with a tangible reference point for understanding the complex processes that shape planetary atmospheres, magnetic fields, and internal structures. Without this close-up perspective, our interpretations of exoplanet data would be far more speculative and uncertain. When we point our most powerful telescopes at an exoplanet and analyze the faint light that passes through its atmosphere, we are trying to decipher its chemical composition. This technique, known as transmission spectroscopy, allows us to identify the presence of various molecules such as water, methane, and carbon dioxide, which can provide clues about the planet's formation history, temperature, and potential for habitability. The distinct signatures of hydrogen, helium, methane, and water that we have measured in detail at Jupiter, Saturn, Uranus, and Neptune. These detailed measurements, obtained through decades of spacecraft missions and ground-based observations, serve as a crucial baseline for interpreting the spectra of exoplanet atmospheres. By comparing the absorption features in exoplanet spectra with those of our own gas giants, we can infer the presence and abundance of various molecules, providing valuable insights into their atmospheric composition and physical conditions. Provide us with a vital reference library. They help us interpret the limited data we can gather from worlds light years away. The challenges of studying exoplanet atmospheres are immense, given the vast distances and faint signals involved. However, by leveraging our knowledge of our own solar system's giants, we can make informed inferences about the composition and properties of these distant worlds, pushing the boundaries of our understanding of planetary systems. Without the detailed knowledge gained from missions like Voyager, Galileo, and Cassini, these missions provided unprecedented insights into the atmospheres, magnetic fields, and internal structures of our solar system's giants. Our attempts to understand the nature of giant exoplanets would be filled with far more uncertainty and speculation. The data collected by these missions have revolutionized our understanding of planetary science, providing a foundation for interpreting observations of exoplanets and developing models of planetary formation and evolution. Furthermore, the diversity we see among our own four giants, the distinction between gas giants and ice giants, has profound implications for the study of exoplanets. The contrasting properties of Jupiter and Saturn, with their predominantly hydrogen and helium atmospheres, and Uranus and Neptune, with their higher proportions of heavier elements, reflect different formation pathways and evolutionary histories. Astronomers have discovered hot Jupiters, massive gas giants orbiting incredibly close to their parent stars, a phenomenon that challenges our traditional understanding of planet formation. These scorching worlds, with orbital periods of just a few days, experience extreme tidal forces and intense stellar radiation, leading to unique atmospheric phenomena and potentially influencing the evolution of other planets in the system. And super-Earths or mini-Neptunes, planets with sizes and masses that fall somewhere between our terrestrial worlds and our ice giants. These intermediate-sized planets are particularly intriguing because they represent a class of objects not found in our own solar system. Their composition and atmospheric properties are still largely unknown, making them a prime target for future exoplanet research. The existence of these exotic classes of planets challenges our simple models of formation. The discovery of hot Jupiters, super-Earths, and mini-Neptunes has forced astronomers to rethink the processes that govern planet formation and migration. These exotic worlds suggest that planetary systems can form and evolve in a variety of ways, leading to a stunning diversity of planetary architectures. By understanding why Jupiter and Saturn are so different from Uranus and Neptune, we can begin to piece together the complex physical processes. The differences in their formation locations, accretion rates, and interactions with the protoplanetary disk likely played a crucial role in shaping their distinct characteristics that lead to the incredible diversity of planetary systems observed throughout the galaxy. The study of exoplanets has revealed a vast array of planetary systems, each with its own unique architecture and composition. From tightly packed systems of multiple planets to solitary giants orbiting distant stars, the diversity of exoplanetary systems is truly astounding. Ultimately, exploring the outer planets helps us answer one of the most fundamental questions of all: are we alone? By studying the conditions that might support life on other worlds, we can gain a better understanding of the potential for life to exist beyond Earth. Many of the moons orbiting our own giants are now considered prime candidates in the search for extraterrestrial life, particularly those with subsurface oceans like Europa and Enceladus. These icy moons, warmed by tidal forces and harboring vast reservoirs of liquid water beneath their frozen surfaces, may provide the necessary conditions for life to arise and thrive. Understanding the conditions that might make these icy moons habitable informs our search for life on a galactic scale. By studying the chemical composition, energy sources, and geological activity of these moons, we can gain insights into the potential for life to exist in similar environments throughout the galaxy. It helps us define the habitable zone not just for Earth-like planets, but for a much broader range of celestial bodies. The traditional concept of the habitable zone, based on the distance from a star where liquid water can exist on a planet's surface, may be too restrictive. Icy moons with subsurface oceans, for example, could potentially harbor life far beyond the traditional habitable zone. Our own gas and ice giants, therefore, are not just planets, they are mirrors reflecting the vast possibilities of what might exist in the cosmos. They are testaments to the diverse processes that shape planetary systems and the potential for life to arise in unexpected places. By continuing to explore and study these fascinating worlds, we can unlock the secrets of the universe and gain a deeper understanding of our place within it. The outer reaches of our solar system are dominated by the gas giants, Jupiter, Saturn, Uranus, and Neptune. These behemoths, composed primarily of hydrogen and helium, possess a gravitational influence that extends far beyond their immediate surroundings. Their immense gravitational presence has played a crucial role in the evolution of our entire solar system, shaping the orbits of smaller bodies, influencing the distribution of matter, and even affecting the very possibility of life on Earth. We often think of the inner rocky planets as the main players in our solar system's story, but the truth is that these distant giants have been silently orchestrating events from afar for billions of years. Their story is one of gravitational dominance, orbital choreography, and cosmic protection, a story that is essential to understanding how our solar system came to be the way it is today. These gas giants, with their swirling atmospheres and vast magnetospheres, are not merely passive observers. They are active participants in the ongoing drama of our solar system, acting as architects and guardians of our planetary neighborhood. They are the silent sentinels, constantly exerting their gravitational influence to maintain a delicate balance within the solar system. Without their presence, the inner solar system would be a much more chaotic and dangerous place, subject to a constant barrage of impacts from asteroids and comets. Their role is not just one of protection, but also of organization, helping to maintain the stability of the planetary orbits and preventing the solar system from descending into complete disarray. Their influence began early on, during the chaotic period of planetary formation, when the solar system was a swirling disk of gas and dust. In this protoplanetary disk, countless collisions and gravitational interactions were shaping the destinies of the planets to come. The gas giants, forming further out from the sun, where temperatures were colder and icy materials were more abundant, quickly grew to enormous sizes, amassing vast quantities of gas and dust. Their immense gravity then began to exert a powerful influence on the surrounding material, clearing out their orbital paths and shaping the overall structure of the solar system. This early period of formation was a crucial time for the gas giants, as their actions would have long-lasting consequences for the entire solar system. The powerful gravity of Jupiter, in particular, is thought to have prevented a planet from ever forming in the region between it and Mars. This region, now occupied by the asteroid belt, was once thought to be a potential site for another planet. However, Jupiter's immense gravitational pull disrupted the accretion process, preventing the smaller bodies from coalescing into a larger planet. The constant gravitational tug-of-war between Jupiter and the Sun kept the material in this region stirred up and unable to settle into a stable orbit. This ultimately led to the formation of the asteroid belt, a collection of rocky and metallic debris that never quite managed to form a planet. Instead, the material in this zone was constantly stirred up and ejected, leaving behind the scattered remnants we now call the asteroid belt. This belt is a testament to Jupiter's gravitational power, a reminder of the planet that never was. The asteroids in this belt range in size from tiny pebbles to massive objects hundreds of kilometers across. They are a diverse collection of materials, representing the building blocks that were never able to come together to form a planet. The asteroid belt is not just a collection of debris, however. It is also a valuable source of information about the early solar system, providing clues about the materials and processes that shape the planets. Jupiter's gravity continues to sculpt the belt today, shepherding asteroids into distinct orbital groups, creating patterns and structures within the seemingly random distribution of these rocky bodies. These orbital groups are formed by the gravitational influence of Jupiter, which pulls on the asteroids and nudges them into specific orbits. The asteroids within these groups often share similar compositions and origins, suggesting that they were once part of a larger body that was broken apart by collisions. By studying these orbital groups, scientists can learn more about the history of the asteroid belt and the processes that shaped it, and creating gaps where stable orbits are impossible. These gaps, known as Kirkwood gaps, are regions within the asteroid belt where there are very few asteroids. They are caused by orbital resonances with Jupiter, where the orbital period of an asteroid is a simple fraction of Jupiter's orbital period. These resonances create gravitational perturbations that destabilize the orbits of asteroids in these regions, causing them to be ejected from the belt. The Kirkwood gaps are a clear demonstration of Jupiter's ongoing influence on the asteroid belt, a constant reminder of the gravitational forces that shape our solar system. More importantly for life on Earth, the giant planets have acted as a cosmic shield, protecting our planet from a constant barrage of impacts from asteroids and comets. Without their presence, the inner solar system would be a much more dangerous place, subject to frequent and devastating collisions. These impacts could have had catastrophic consequences for life on Earth, potentially wiping out entire species and preventing the emergence of complex life. The giant planets, therefore, play a crucial role in maintaining the conditions necessary for life to thrive on our planet. The outer solar system is home to countless comets and asteroids, icy bodies left over from its formation. These objects, residing in the Kuiper Belt and the Oort cloud, are remnants of the early solar system, providing valuable clues about the conditions and materials that existed at the time of planetary formation. They are essentially time capsules, preserving the pristine materials from which the planets were formed. These icy bodies are constantly being perturbed by the gravitational influence of the giant planets, sending some of them on trajectories towards the inner solar system. Without the gravitational influence of Jupiter and its siblings, many more of these objects would have careened into the inner solar system, posing a significant threat to Earth and the other inner planets. Jupiter's immense gravity acts as a sort of gravitational barrier, deflecting many of these incoming objects away from the inner solar system. It either slingshots them out of the solar system altogether or redirects them into safer orbits. This gravitational shielding effect is crucial for maintaining a relatively stable and safe environment for life on Earth, leading to a much higher rate of catastrophic impacts on Earth. These impacts could have triggered mass extinctions, altered the climate, and even sterilized the planet, making it uninhabitable. The frequency of these impacts would have been significantly higher without the protective presence of the giant planets, making the emergence and survival of life on Earth much more challenging. The Earth's history would have been drastically different, and we might not be here today if it weren't for the cosmic shield provided by Jupiter and its fellow gas giants. Jupiter, with its enormous gravity well, acts like a giant celestial vacuum cleaner, sweeping up and deflecting countless asteroids and comets that would otherwise pose a threat to the inner solar system. Its gravitational pull is so strong that it can capture objects from the outer solar system and redirect them into new orbits, preventing them from ever reaching the inner planets. This gravitational cleaning effect is a crucial aspect of Jupiter's role as a protector of Earth, deflecting or capturing many of these potential impactors, preventing them from colliding with Earth and causing widespread devastation. This gravitational capture can sometimes lead to the formation of new moons around Jupiter, as captured asteroids become gravitationally bound to the planet. The process of deflection, on the other hand, involves altering the trajectory of an incoming object, sending it on a path that avoids the inner solar system. Both of these processes contribute to Jupiter's role as a cosmic protector. While impacts still happen, as evidenced by the occasional meteor streaking across our sky, their frequency has been drastically reduced thanks to the protective presence of our solar system's largest planet. These impacts serve as a reminder of the constant threat posed by asteroids and comets, but they also highlight the effectiveness of Jupiter's gravitational shielding. Without Jupiter, the rate of impacts would be significantly higher, and the consequences for life on Earth could be dire. The gravitational dance of the giant planets may have also been responsible for a dramatic and violent chapter in our solar system's history, a period of intense bombardment that reshaped the surfaces of the inner planets. This dance, involving complex gravitational interactions and orbital migrations, is thought to have triggered a cascade of events that led to a significant increase in the number of impacts on the inner solar system. Understanding this period of intense bombardment is crucial for understanding the evolution of the inner planets and the conditions that allowed life to emerge on Earth. known as the Late Heavy Bombardment. This period, which occurred approximately 4 billion years ago, was characterized by a dramatic increase in the number of asteroid and comet impacts on the inner planets, including Earth, the Moon, and Mars. The evidence for this bombardment can be seen in the heavily cratered surfaces of the Moon and other ancient planetary surfaces. The Late Heavy Bombardment was a significant event in the history of the solar system, shaping the surfaces of the planets and potentially influencing the conditions for life. Some modern theories, like the NICE model, propose that the giant planets did not form in their current orbits, but instead underwent a period of migration that triggered the Late Heavy Bombardment. The NICE model suggests that the giant planets initially formed closer together in a more compact configuration and then gradually migrated outwards over time. This migration would have disrupted the orbits of asteroids and comets in the outer solar system, sending them on a collision course with the inner planets. Instead, they may have formed closer together and then migrated over time, driven by gravitational interactions with the surrounding disk of gas and dust. As the giant planets migrated outwards, they would have encountered and interacted with a vast population of icy bodies in the outer solar system, scattering them in all directions. Some of these scattered objects would have been flung inwards towards the inner solar system, leading to a surge in the number of impacts on the inner planets. This migration would have been a chaotic process, with their shifting gravitational fields disrupting the orbits of countless smaller bodies in the outer solar system. The gravitational interactions between the giant planets and these smaller bodies would have been complex and unpredictable, leading to a period of intense orbital instability. This instability would have resulted in a significant increase in the number of objects being ejected from the outer solar system and sent on trajectories towards the inner planets, destabilizing the orbits of vast numbers of asteroids and comets in the outer system, flinging them inwards towards the inner planets and triggering a period of intense bombardment. These destabilized objects, no longer confined to the outer solar system, would have rained down on the inner planets, creating a period of intense cratering and geological upheaval. The Late Heavy Bombardment would have had a profound impact on the surfaces of the inner planets, shaping their landscapes and potentially influencing their atmospheres and oceans. This would have triggered a massive spike in impacts throughout the inner solar system around 4 billion years ago, a period of intense bombardment that left its mark on the surfaces of the Moon, Mars, and even Earth. The evidence for this bombardment can be seen in the numerous craters that cover the surfaces of these celestial bodies, providing a visual record of the violent events that occurred during this period. The Late Heavy Bombardment was a transformative event in the history of the solar system, shaping the evolution of the inner planets and potentially influencing the emergence of life on Earth. A bombardment that scarred the Moon with countless craters and may have delivered water and organic compounds to the early Earth, providing the building blocks for life. The impacts during the Late Heavy Bombardment would have released vast amounts of energy, melting the surfaces of the planets and creating new geological features. These impacts may have also delivered volatile compounds, such as water and organic molecules, to the early Earth, providing the raw materials necessary for the emergence of life. The Moon, with its heavily cratered surface, serves as a stark reminder of the intensity of this bombardment and its potential role in shaping the conditions for life on Earth. From shaping the asteroid belt, preventing the formation of a planet between Mars and Jupiter, to protecting the inner planets from a constant barrage of impacts, and possibly delivering the building blocks of life to Earth, the giant planets have played a pivotal role in shaping our solar system. Their gravitational influence has been a constant force, shaping the orbits of smaller bodies, influencing the distribution of matter and creating the conditions necessary for life to emerge and thrive on Earth. Their story is one of cosmic proportions, a testament to the power of gravity and the interconnectedness of the solar system. The influence of the gas and ice giants is woven into the very fabric of our solar system's history, shaping its architecture and influencing the evolution of life on Earth. They are not just distant observers, but active participants in the ongoing drama of our solar system, constantly exerting their gravitational influence to maintain a delicate balance. Their story is one of cosmic proportions, a testament to the power of gravity and the interconnectedness of the solar system. They are not isolated worlds existing in a vacuum, but integral components of a complex, interconnected system, where gravitational forces and orbital dynamics play a crucial role in shaping the destinies of all the planets. The giant planets are constantly interacting with each other and with the smaller bodies in the solar system, creating a complex web of gravitational relationships. These interactions can have significant consequences for the stability of the solar system and the conditions for life on Earth. Their formation, their migration, and their sheer gravitational might have dictated the final architecture of our planetary family, shaping the orbits of the planets, influencing the distribution of matter, and creating the conditions necessary for life to emerge on Earth. Understanding their role is essential for understanding the history of our solar system and the processes that led to the formation of our planet. Understanding their role is essential to understanding our own origins and the long, complex chain of events that ultimately led to the emergence of a habitable world like Earth. By studying the giant planets, we can gain valuable insights into the processes that shaped our solar system and the conditions that allowed life to arise on our planet. Their story is intertwined with our own, and understanding their role is crucial for understanding our place in the universe. That ultimately led to the emergence of a habitable world like Earth, a planet teeming with life and capable of supporting complex ecosystems. The giant planets, with their gravitational influence and their role in shaping the solar system, have played a crucial role in making Earth the habitable world that it is today. Their story is a testament to the interconnectedness of the solar system and the delicate balance of forces that allows life to thrive. They are the silent, distant guardians that made our existence possible, the unseen architects of our solar system, and the protectors of our fragile planet. Their story is a reminder of the vastness and complexity of the universe and the delicate balance of forces that allows life to flourish. They are the silent giants, watching over us from afar, ensuring the continued stability and habitability of our solar system. The outer solar system, a realm of colossal planets and icy moons, holds secrets that have captivated scientists and dreamers alike for generations. Our exploration of this distant frontier is not just a series of missions and discoveries. It's a story, a grand narrative that is still being written, with each new observation adding another layer of complexity and wonder. It's a story of perseverance, of technological innovation, and of our unyielding curiosity about the cosmos. We stand at the precipice of a new era of exploration, poised to unlock the mysteries of these giant worlds and their potential to harbor life. The journey is far from over. In many ways, it's just beginning. Every spacecraft we launch, every instrument we deploy, every signal we receive from across the vast gulf of space adds a new brushstroke to this ever-evolving portrait of the outer solar system. Each mission we send, each new piece of data we gather, adds a new chapter to this unfolding saga of discovery. We meticulously analyze the data, piecing together the puzzle of these distant worlds. We scrutinize the images, searching for clues about their formation, their composition, and their potential for habitability. It's a painstaking process, but the rewards are immeasurable. With each new finding, we refine our understanding of the universe and our place within it. The seeds of this grand exploration were sown decades ago, with the daring voyages of the Voyager spacecraft. What began as a grand tour by the Voyager spacecraft in the 1970s and 80s, a bold mission to visit Jupiter, Saturn, Uranus, and Neptune, has evolved into a dedicated long-term investigation, a sustained effort to unravel the mysteries of the outer solar system. These pioneering probes provided our first close-up views of these distant worlds, revealing their stunning beauty and hinting at the secrets they held. Their legacy continues to inspire us today, as we push the boundaries of exploration even further. Following in Voyager's footsteps, the Galileo mission embarked on a dedicated study of Jupiter and its moons. The Galileo mission spent years in orbit around Jupiter, braving the planet's intense radiation belts to reveal the secrets of its moons, particularly the intriguing possibility of subsurface oceans on Europa. It was a groundbreaking mission that transformed our understanding of Jupiter's complex system and paved the way for future exploration. Galileo's discoveries ignited our curiosity about the potential for life beyond Earth and fueled our desire to explore these icy worlds in greater detail. Then came Cassini-Huygens, an ambitious international collaboration that revolutionized our understanding of the Saturn system. The Cassini-Huygens mission revolutionized our understanding of the Saturn system, unveiling the astounding complexity of its rings, a dazzling spectacle of ice and rock, and landing a probe on the surface of its mysterious moon, Titan, a world with lakes of liquid methane and a thick, hazy atmosphere. Cassini's long and fruitful mission provided a wealth of data about Saturn, its rings, and its moons, transforming our perception of this distant world and its potential for harboring prebiotic chemistry. The Huygens probe's descent to Titan was a triumph of engineering and a testament to our ability to explore even the most challenging environments. These missions, each with its own unique objectives and discoveries, transformed our perspective, turning these distant worlds into familiar, albeit alien landscapes. We began to see them not as mere points of light in the night sky, but as real places with their own unique geology, atmospheres, and potential for harboring life. These missions have fueled our imaginations and inspired us to dream of a future where humans can explore these distant worlds firsthand. And the quest for knowledge doesn't stop there. Today, the journey continues, with new missions pushing the boundaries of exploration and revealing even more about the outer solar system. The Juno spacecraft is currently in a daring polar orbit around Jupiter, a unique vantage point that allows it to probe the planet's depths in unprecedented detail. Flying closer to its stormy cloud tops than any mission before it, Juno is providing us with a wealth of new information about Jupiter's atmosphere, magnetic field, and internal structure. It's a challenging mission, but the rewards are well worth the risk. Juno is on a mission to unravel the mysteries of Jupiter's interior, peering deep beneath the planet's dense atmosphere to map its magnetic and gravitational fields, seeking to understand the nature of its core and the engine that drives its powerful internal dynamics. By studying these fundamental properties, Juno is helping us to understand how Jupiter formed and how it has evolved over billions of years. Its findings are providing valuable insights into the formation and evolution of gas giant planets throughout the galaxy. But Jupiter itself is not the only target of our curiosity, and we are already planning our return to the moons of Jupiter, particularly Europa, Ganymede, and Callisto, which are believed to harbor vast subsurface oceans. These icy moons are among the most promising places in the solar system to search for life beyond Earth. The upcoming Europa Clipper and Jupiter Icy Moons Explorer, or JUICE, missions are specifically designed to investigate the tantalizing possibility of subsurface oceans on Europa, Ganymede, and Callisto, taking us one step closer to answering whether these worlds could harbor life. These missions will employ a variety of sophisticated instruments to probe the moon's icy surfaces and subsurface oceans, searching for evidence of liquid water, organic molecules, and other signs of habitability. The data they collect will help us to assess the potential for life on these distant worlds and to understand the conditions necessary for life to arise elsewhere in the universe. Yet, despite these incredible advances, despite all that we have learned, vast mysteries remain, lurking in the shadows of the outer solar system, waiting to be uncovered. The ice giants, Uranus and Neptune, those enigmatic blue worlds on the fringes of our solar system, remain the most poorly understood planets in our solar system. Their distance and relative lack of exploration have left us with many unanswered questions about their formation, composition, and atmospheric dynamics. They have each received only a single fleeting visit from a spacecraft, a brief flyby by the Voyager probes decades ago, and our knowledge of them is filled with fundamental questions. These brief encounters provided tantalizing glimpses of these distant worlds, but they were not enough to fully understand their complex nature. What is the source of Neptune's incredible internal heat and dynamic weather, which generates some of the fastest winds in the solar system? This excess heat is a puzzle that scientists are still trying to solve. What cataclysmic event gave Uranus its extreme tilt, causing it to rotate on its side, almost perpendicular to the plane of the solar system? This unusual orientation is a major mystery that has puzzled astronomers for decades. What are their dark, enigmatic rings made of, those faint and mysterious bands of particles that encircle these distant worlds? Their composition and origin remain largely unknown. To answer these questions, the scientific community is advocating for new dedicated orbiter missions to these distant blue worlds, recognizing that they hold unique clues about a class of planet that may be incredibly common throughout the galaxy. These missions would provide long-term observations of Uranus and Neptune, allowing us to study their atmospheres, magnetic fields, and internal structures in detail. This is the nature of exploration, the endless cycle of discovery and inquiry. Every answer we find seems to unveil a dozen new questions, each more compelling than the last, driving us to push the boundaries of knowledge even further. It's a testament to the human spirit, our insatiable curiosity, and our unwavering desire to understand the universe around us. The giants of gas and ice beckon us forward, promising discoveries that could once again revolutionize our understanding of how planets work, how solar systems evolve, and what conditions are necessary for life to arise, not just in our solar system, but throughout the vast expanse of the cosmos. Our journey to the outer solar system is more than just a scientific endeavor. It is a fundamental part of the human quest to understand our place in the universe, to unravel the mysteries of our origins, and to explore the possibilities of life beyond Earth. It's a journey that requires courage, innovation, and a willingness to embrace the unknown. And so, our story begins not with an ending, but with an invitation to join the voyage, to venture into the cold, the dark, and the beautiful realm of the giants, to explore the wonders of the outer solar system, and to discover the secrets that await us there. It's a journey that will challenge us, inspire us, and ultimately transform our understanding of the universe and our place within it. As we conclude our journey through the majestic outer planets, we invite you to continue exploring the cosmos with us. What aspects of these giant worlds fascinated you most? Perhaps Jupiter's great red spot, Saturn's magnificent rings, or the potential for life on moons like Europa and Enceladus? Share your thoughts in the comments below. If you enjoyed this cosmic voyage, please consider subscribing to our channel for more documentaries about our solar system and beyond. Each like and share helps us bring the wonders of space to more curious minds across our planet. Stay tuned for our upcoming explorations of dwarf planets, comets, and the mysteries at the edge of our solar system.